Very good afternoon to everyone, and welcome to this INBIOSIS-MSBMB webinar lecture series, second one in this year, talk about structural biology. And I'm your moderator today. I'm Leong, Research Fellow in Institute of Systems Biology, INBIOSIS, and also Secretary for the Malaysian Society for Biochemistry and Molecular Biology. And I hope just now some video play will provide you some background of our institute for INBIOSIS. And for those who are interested to collaborate with us, you're most welcome to contact us. And feel free to browse INBIOSIS website and also MSBMB website to know more about the society as well. And I feel so grateful today so that we are having a chance to have Prof Chen here with us, and also to have every one of you here join in this webinar. So I hope that the collaboration between the INBIOSIS and MSBMB will also bring more informative and knowledge sharing webinar to us. So there will be more to come in the coming future. So I hope you all will join again in the coming future. INBIOSIS webinar or series is established to provide knowledge and research experience, sharing platform to ensure we are still connected with each other and stay motivated in our research despite this challenging time of pandemic. I think, in fact, it has connected us even more closer than before, because the platform that we use from this virtual and allow us to organize an event like this. So I present INBIOSIS and also MSBMB today to welcome Prof Chen joining us in this event, and for his kindness for sharing with us. So during this webinar, I have some housekeeping rules. The lecture will take about 45 minutes, and following by the Q&A section. And for 15 minutes, if there's more interesting question, Prof Chen already agreed that he will continue to answer if there are more questions. Please submit the questions in the Zoom chat box or the FB Live page. So I will read the questions during the Q&A section. And before the seminar ends, I also would like to invite all the participants to switch on the camera for the photography sections. And please still stay tuned until the end of the section to fill in the attendance form for e-certificate and as well for UCAM credit. And without further ado, I would like to introduce our honorable speaker today, Prof. Dr. Chun-Jung Chen from National Synchrotron Radiation Research Center, NSRRC, Taiwan. And I would like to share with you the background of Professor Dr. Chen. Prof Chen has a long-standing background in structural biology, biochemistry, and biophysics, particularly in the synchrotron protein crystallography and X-ray techniques. Prof Chen obtained his bachelor and master degree from National Tsinghua University, Taiwan, and graduated for his PhD from the Department of Crystallography, University of Pittsburgh, United States in 1999. Before returning to Taiwan to join National Synchrotron Radiation Research Center and NSRRC in 2001, he was a postdoctoral fellow in Department of Biochemistry and Molecular Biology at University of Georgia. Prof. Chen is currently a Deputy Director for NSRRC and a scientist in the Life Science Group in NSRRC. He's also a joint professor in Department of Biological Science and Technology, National Chiao-Tung University, Department of Physics, National Tsinghua University, and National Chun-Jung University. Prof. Chen also actively involving and contributing to the national and international activity and the service. For instance, he sits on the Scientific Advisory Board of Thailand Protein Society, International Advisory Committee Board, and international expert for Alagaba University, India, and a council member for the Asian Crystallography Association and International Union of Crystallography, and a long list of contributions that Prof. Chen have done to the community, and also a reviewer for many journals, including like Journal Medical Chemical, Journal Biology, Chemistry, Scientific Report, and so on. And Prof. Chen also awarded with NSC Outstanding Young Scholar Research Project in from 2011 to 2015, and also a research he have his research on the press or media in 2015, 2018, and recently 2019 for his work in shrimp nodavirus, which I think he's going to share with us today. And Prof. Chen has published more than 100 papers in renowned journals, including JACS, Plus Pathology, Journal of Medical Chemistry, JBC, JMB, and many. IUCR Journal, ACTA-D, and many other journals. So I think without further ado, let us have a warm welcome for Prof. Chen to share his research finding and talk to us about the synchrotron in Taiwan as well. Thank you, Prof. Chen. The Zoom is yours. Welcome. Prof. Chen, I think you are mute.
Okay. Thanks, Professor Leong, for the kind introduction. I'm great here to share my research, and I want to introduce you some of our facility as National Synchrotron Research Center. And this will be a public facility, provide all kinds of research opportunity for all of you. And I want to take this chance to thank you for attending this lecture. And I'm happy to answer all the questions after my talk, or during my talk, if you have any short question, I can also answer. So shall I start or? Okay. So how do I start? Can I hear you?
Want to share the screen like just now?
Yeah, I share. Okay.
Yeah.
Okay, so this is my talk. Today, I'd like to focus on the viral structures and then some opportunities of the structural biology at NSRRC. So you can see this is the National Synchrotron Radiation Research Center. So as you can see, this is a synchrotron facility in the world, and you can see in from this side, and European, and then Asia, and then all the way to American side. So Taiwan is located here. It's number 15. You can see, and I noticed Malaysia is here. So you're sitting here. We are not far away from each other, and so I'll give you some geography idea that Taiwan is this area, and then the synchrotron Radiation Research Center is located in Hsinchu, which is the north side of the Taiwan. So if you fly in from Malaysia to Taiwan, you can come. I think the international flight is in Taoyuan here, so it's not far from the Hsinchu. So only like 40 minutes you can reach to Hsinchu. So if you bring your sample, you can come into the synchrotron for your research. So this is our campus. So you can see the two rings. There's one ring. There's a campus surrounded by the national. This is the very famous science park in Hsinchu, and all the semiconductor and the TSMC companies here. We are doing a lot of the high-tech business here. And NSRRC is located in inside the park and surrounded by two universities. One is the Jiao Tong University, and another one is the Tsinghua University. So this campus is surrounded by a very high-tech area. And so you can see two rings. This is a TOS, Taiwan Light Source. This is already there for more than 25 years, open to the user in 1994. And this is a new so-called Taiwan Photon Source, TPS. This is just opened in 2016. And it's a new ring, new synchrotron ring, and better capacity and better performance. And I will introduce you some of the facility inside. So let me give you some idea about the history. And so the synchrotron is NSRRC was founded in 1980s, and in 1994. And we have the first bin open, and then 94 we have open to the user here. And so after 20 years, and the users and the government think the capacity is not enough and to accommodate all the users and the scientific needs. So we start to collaborate with Spring A in Japan, and we build two bin lines in 98, and this two bin lines still open to users, but Taiwan need a local new synchrotron. So in 2010, we start to construct a new TPS. So after 3 years, and then the civil construction is finished, and 2014 we have the first bin line open to store, and then 16 we have the open some bin lines to the users. So this is some history. And you can see from the satellite map on the left-hand side here. And so from the satellite imaging, you can see the NSRRC campus is here. And you can see the small ring, which is a TOS in 2010. And in 2013, you can see the new ring coming up here. So this is the TPS ring. Okay. So this is about the history of the NSRRC. And I'd like to show you some imaging when this TPS was during the civil construction from 2010 to 2013. The end of 2013 is almost 1,001 days. So I'd like to share you some very memory imaging here. So this is our research building, and I start. So this ring was surrounding this research building, and the O-ring TOS is here. Oh, sorry. So you can see that surrounding this building, and my laboratory is inside on this corner here. So during the construction, I had to go in different approach to this building, to my lab. So from time to time, I had to change the route. And eventually, you can see this ring was below the ground on this side. because the ground level is not even. So this is a sorry. Okay, so after this TPS was constructed, and we received a lot of congratulations and greeting from the world, and then was receiving a lot of reports from the journal. And in 2015 is a year of lights, and then you can see many publications and using the journal using our campus photo as a cover imaging here, so introduce the synchrotron science. So our TPS is really attract international attention, and so because this is a very bright, providing a bright X-ray and for the research. So right now, NSRRC has several facilities, and then including the TPS and TOS I just introduced. And inside there's a bin nice. I will tell you later. And then, but beside these two rings for the X-ray, we have a neutron facility, because of Taiwan now we don't have the neutron facility for research, and so we have the collaboration with Australia and NSTO, and using the NSTO facility build bin lines, and this bin lines for the physics and the material research. And so the user can fly from Taiwan to Australia. This is near the Sydney area in the east to do the research. And also the two bin lines, I just introduced that we have two Taiwan contract bin lines in Spring and Japan, and this is still operating. For right now, it's almost 20 years, and we still continue. So this is all the facility we have by NSRRC. So if you get the cross loop, you can see this TOS ring and the TPS ring. So you can see here on the loop, we have the solar panel here to generate the electricity. And so you can see all the solar panels on the roof. And so our mission is the building the bin lines and different bin line capacity for the users. So right now the TOS, the old ring has a 23 bin lines, and then we hope those bin lines will gradually move to the capacity move to the new rings, the TPS, because of better performance. And so we have the bin line construction since 2013. And so we have the first, we call the phase 1 and phase 2 and phase 3 bin lines. And phase 1, we have seven bin lines. And this is open already in 2016. And then phase 2 bin line, we will have 9 bin lines. And this is we have project to finish this year, but some of bin lines are already open. So right now we are in the final stage of the phase 2 bin line. So after that, we have the 16 bin lines plus 1 for brain imaging bin lines. And then this year we kick off the phase 3 bin lines. We will start to construct 9 new bin lines, and we will project to finish in 2026. So by 2026, we will have 25 bin lines plus 1 PRT brain imaging. This is a bin lines for the brain imaging, and collaborate with Tsinghua University Life Sciences Department. So if you look at the TOS, you can see that this is the O-ring, and inside the bin lines very crowded, and then this is already open for 25 years, and it's pretty much occupied. And but at least some of the bin lines facility for life sciences, and such as protein crystallography, small angle scattering, and cellular cohesion, and the membrane scattering, or X-ray microscope and the IR beam lines. And those are very good facility for the life sciences. For example, if you look at the right side, this is nature cover. This is a dinosaur fossil imaging using the IR beam line. You can see this is the first time to see some organic remaining in the fossil, the dinosaur fossil. So it is on the cover page of the Nature. It's produced by our beam lines. So for the TPS, we have as I say, we have the phase 1 and phase 2 beam line. And so we are in the final stage of the phase 2. And hopefully we'll have this is the 6+1, so 9 beam lines, and then 7 beam lines. And so we have this the map, and so it's already most of them are already open to the user, and so still some of the under commissioning, and the red one is opening. And so as I say, today I want to introduce you some of the crystallography beam line. So we have 05 is a protein crystallography beam line, and then we have the phase 2. We have the second beam line, so-called the microfocus protein crystallography beam line, will be ready the end of this year and to open to the user. Okay, so this is a new beam line. So I want to share you some of our international user distribution, and this is a statistic based on the 2019. Last year, because of COVID-19, we don't open for the international user. So I use 2019 as a statistic to show you how popular our facility is. So this is Taiwan is here, and you can see that from different countries, from European, Asia, and South Asia, and Australia, and United States, and Canada. So we attract many users. So it's around 17% international users coming to Taiwan to do the research. So it's a percentage is quite high. So hopefully we can reach to 20%. And we welcome you to come over here, Taiwan, to do your research. And this is a proposal based on the field. And you can see the large field is material science. And second one is the protein crystallography, structural biology, and then some surface interface, thin film, and soft matter also include the proteins and chemistry, and then environmental science, and some of the proposals for industrial research. Okay. So this is a publication that we have using the user using our facility to produce a paper. You can see this is from we do the statistic from back to 1997. You can see this keep increasing, and until recently, 2019 and 2020 last year. So all we have over 472 publication. Among that, we in the top 5%, we have 200 papers, and then top 10, 300, and top 15, 370 papers. So you can see the percentage is quite high. We see the impact increase if you use a synchrotron light for your research will definitely increase your impact and your research. So you can see if you count using the impact factor of the journal, you can see from 2014 to 2020, you can see an impact factor increased a lot until last year. We had the average impact factor reached to 8.2, 8.1. So you can see the synchrotron really benefit the research. So again, I welcome you to use using the facility, and the best about if you use the facility, it's free. We don't charge you for the using the beam line or the light source, but we ask you to publish your paper to acknowledge our facility. So this is a mutual benefit that you can get the good light source for your research, and we'll get the publication application, and then we can provide a better service and with the funding. So this is again, this is a total the binline map we have in the future until 2026. So as I say, phase 1, phase 2, and phase 3 binlines, and so we're pretty much occupied. And so different color, the blue color represent the phase 1, and green color the phase 2 binlines, and the red color is the third binline, phase 3 binlines. So we are because of budget issue that we have 3 phases, but I think we are in a very steady progress to make this binlines all fully functioning. So this is a brief introduction about our facility, that I hope that our facility and to open up some new opportunity for you, especially for the structural biology and research. So in the next, I will show you some of the applications and some of the research. So using this facility, you can study your material or your cell by imaging. Or if you want to study the structure, you can using the scattering or diffraction, and such as virus structures and the membrane proteins, and some of the drug-based, structure-based drug design. And spectroscopy, you can measuring some metals in your protein or in your sample. You can because the synchrotron energy can be tunable, so you can cover a lot of the range to measuring the different atoms, especially metal in your sample. So spectroscopy binline is very particularly useful for this kind of research. So I list some of the TPS binline related to the life sciences for your reference. And the first is protein crystallography. You can study the membrane protein and the large protein assembly, or even the virus structure that I'll talk about later. And this is a benefit by the Z05 protein crystallography binline. And or you can using the this is a powder diffraction binline. You can measure some drug structures and small molecules. And then you have the you can use BioSAX. This is small angle scattering binline. You can measure in the rough shape of your protein molecules, and you can get the idea of how the envelope of your protein, and how this the good thing is you can measure in the solution states, that such as you can measure in dynamic and the structure changes during the different condition using the small angle scattering. And you can use the absorption spectroscopy. You can measure in the metal in the structures by detecting the absorption of the metal. And imaging, you can measuring the tomography and of the cell imaging, mitochondrial and some organelle in the cell. So this is what we have for the life science: protein crystallography, small angle scattering, absorption spectroscopy, and then X-ray imaging. You can measuring large assembly protein and the membrane protein, material protein, and solution structure, drug design, and some bioimaging. Okay. So because of time limits, I only can give you some introduction or lecture on this protein crystallography today. So today, my focus will be using this protein crystallography binline to study the virus structure. So what's the protein crystallography? For you, I like using this page to give you some idea what we do for protein crystallography, what experiment they will perform, and to reach the structure. So first, you need to decide what the protein target you want to study, and like you can purify your protein. And the protein purification, you can purify your protein from the natural source, or you can use the molecular cloning to do the overexpression to get the recombinant protein, and then hopefully you can get the single very pure protein. On the SDS page, you will see a single band and without much contamination of other proteins. Okay, and after that you can go to the second stage, crystallization. This crystallization is some kind of the trial and error because the condition is unknown. So we have to add some chemicals into the protein solution and do some strategy to persuade the crystal grow. And so this is kind of the condition screening trial and error method. And after that, you have to optimize the condition to get the good quality crystal. The size of the crystal is about a 0.1 millimeter size. So it's very small because the protein is relatively small. So the protein crystal is also small. So you need to observe the crystal grow under the microscope. And some people 0.2 millimeter in dimension. Okay, so after you get the crystal, and you can bring the crystal, you can fish the crystal and frozen the crystal in the liquid nitrogen, and using the X-ray, synchrotron X-ray for the diffraction. And because of this crystal inside, there's a lot of protein molecule arranged periodically. So we use X-ray diffraction to get the electron information. So this is the diffraction imaging. So all the diffraction imaging has information of the electron. So we need to do the calculation and to extract the imaging of the electron density in three-dimensional arrangement. And after that, you can see the electron density map, and this corresponding to your sequence amino acid. So we need to build a model, and based on your density map. And after that, you can do the refinement to fit the density with your structure, and for the better agreement. And then you can decide the overall structure, determine the overall structure, and then you can look at the substrate or product or any ligands and or any complexes, and they can study the important residues, and then do the mutagenesis, and then to prove the biochemistry data, and then hopefully you can go to the later applications, okay, like drug design or medical biotech applications. So this is a overall protein crystallography protocol that you need to follow, from the protein purification, crystallization, and synchrotron X-ray diffraction, and then the electron density calculations, and then determine the structures and the application. Of course, publication is important. So you need to publish your work. Okay. And I show you, this is some example that we perform in the synchrotron. This is a crystal that you see, the crystal here. And this crystal, because crystal is small, we use a loop, and then to fish out the crystal from your crystallization drug. And this is a different crystal with a color, because this protein contains the iron in the inside. So when you crystallize the protein, it will become a reddish color, like a ruby crystal. Okay, so the square represent the X-ray beam, and you can hit the crystal and then get the diffraction data. So this is the photo I took with my lab member, and then this is during the midnight 2:30 in the, I don't know, it's the morning or night. So we work because synchrotron light is a 24-hour operate. So we need to do the experiments when we have the beam time. We need to perform using the beam light wisely, and then so day and night we had to use this beam light. So we can see these two colleagues are very tired, and then they take a nap during the data collection. But I think from my experience, when we in the nighttime is the best time to get the good data, because no any interruption, and we can get a nice data set. Okay. I can skip this one later. So let me get to the virus structure now. And so today I want to introduce you some of the virus family we call the Notaviride family. This is the family Notaviride is a kind of virus to infect three kind of species. One is we call the alpha notaviruses infect the insect, and beta notavirus second infect the grouper fish, and the third one notavirus infect the shrimp. So today I want to introduce you two of the virus. One is the beta notavirus. One is unassigned. This is a new assigned notavirus. We just categorize this sort of structure. So the first I want to introduce you the beta notavirus. This is a group. This is, you can see the fish. This is a big group of fish. We call the orange spot grouper. You can see the orange spot on the surface of the grouper. Okay, but this virus, nervous necrosis virus, we call the NNV, infect this grouper, and this virus is a non-envelope virus. Its dimension of this virus is 30 nanometer size, and it's a it's a single strand positive sense RNA virus. So during the infection, especially in the younger stage of the fish, and the virus will attack, and then it will attack the central nervous system of the fish, younger fish, and such as the brain, and spindle, and core, and eyes, and then it will cause the fish abnormal behavior like a spinning, swing, or the muscle tremor, and so it causes the fish high mortality. It's almost 100%. So right now there's no any other way to prevent, but most of the fish farm use a depopulation because they put they have the several farm to separate those depopulation, and so to reduce the risk of the infection. So this is all the infections. So I show you this is a video I found from the YouTube. This is the tank in the tank of the young groupers. So this already died, and this fish was got infected. You can see it's swimming and upside down. And eventually the fish will die, and not just die, but the virus will spread out all the tank to infect all the fishes, and then eventually the mortality will be cause all the fish die. So we are able to purify this capsid protein of the virus, and this is we're using the EM electron microscope, negative staining EM, to see the virus particle, and this is a particle size about 30 nanometer, and so but the resolution is low, so we like to see all the structure, or because the higher resolution give the better detail the information for studying this virus. So so we took those viruses solutions, and then we crystallized the virus particle. You can see on the right hand side, this is a crystal of those virus. So a lot of viruses is assembly and arranged inside the crystal here. Okay, but still you cannot see the virus in detail. So we need X-ray to help us to see every single atom of the virus. So we use a synchrotron light source by using the protein crystallography method, and this is the bin line we have because I think structural biology is very important for the life science, and especially for not just life science but the whole science. So in our synchrotron we have the several bin lines for structural biology study, especially protein crystallography. So this is a TOS bin line, and we have 3 bin lines. And then this is the TPS new ring. We have the first bin line 058. This is the phase 1 bin line and open to user in 2016. So we use those bin lines for for X-ray diffraction. And this is the closed loop of the beamline. So this is the detector, and then X-ray coming from this direction, and then shoot the crystal, and then detect on this detector here, and transfer the imaging diffraction data outside the computer to processing. If you look at the other beam lines, this is a TLS beam line. The X-ray coming from this direction, and so the crystal should put it here, and then during the data collection, this is the diffractometer will rotate the crystal, and this is a detector here to collect the diffraction data, and this is a cryo cooler because synchrotron X-ray is very strong, so we need to protect the crystal by cooling the crystal in near the liquid nitrogen temperature, minus 160 below 160 degrees. So you can see the loop. There's a crystal on the loop. So the crystal should be sitting on. If you look at the right side, here, this is the cryo stream, cool the crystal, and X-ray coming from this direction. And this is a direct beam stop, and the crystal here, you can put it here under the direct beam here. So after you collect the data and this data imaging, so you need to do some processing, and then to calculate the electron density law function. And you don't need to know the mathematics. Just jump this straight. And after this calculation, you will get the electron density map. And this electron density map allows you to build all models of the H amino acid based on your sequence. And then you can build all the structures and for your study. Okay, so this is after you collect the data, you need to do some calculating computer work, and then to build your protein model. So for virus structure, we're using the spatial way to calculate the electron density map. This is a 25 angstrom resolution. That means that you can see the detail in 25 angstrom. So this is viral structure, but it's not in great detail yet. But you can see the overall shape. This is 22 angstrom resolution. And this is a 4.7 angstrom resolution. You can start see something very clear on the protrusion here. And this is 3.2. You can see the particle is not spherical. In fact, there's a spike on the surface here. Okay, so if you cut this spherical particle half, you can see the inside is empty. This is like a shell, the capsule shell of the virus. The inside is a open space for accommodate the genome inside, but because we're using the overexpression way method we don't use we use a virus-like particle, not a mature virus. So inside contain no genome. It's not it's a virus-like particle. So when you determine the structure, you don't see the empty inner cavity filling up genome, but rather is a empty space. But you can see the beta strand structure. You can see some strand structure character very well. So based on that, you can build your model. And this is I like to mention that this particle was assembled by 180 single capsid protein. So to form the whole complete particle, dimension is over 350 angstrom, so it's 35 nanometers. And this is a 180 capsid protein assembly into the particle. So when you determine the structure, you can see that every capsid protein structure looks like this, containing the P domain and S domain and the N-terminal arm domain here. And you can see when you see inner cavity 200 angstrom, and this is the protrusion domain. and it's an surface domain here. Okay, so we can see every single atom of the virus. So not just that, when you compare the sequence of the different groupers viruses, you can see they are especially in the P domain. You can see the variable region here. This is based on the sequence alignment. You can see all the variable region was occurred in the P domain. So this is the P domain structure here, and located protrude outside the surface. So the red part corresponding to the variable region. So this P domain is really give evidence that is associated with the receptor binding or the host cell specificity during the virus infection. So because it's in the protrusion domain, all the different virus for different species like a orange box grouper, dragon grouper, or red spot groupers, they all have the different virus species with a different P domain sequence. And this is the variable residues all exist in the protrusion domain here. So this is the first contact of the fish cell. And so the protrusion surface is responsible for the receptor binding and the host cell specificity. So based on this structure, we can conclude that. So we first in 2015 we determined the first group beta norovirus structure, and this we can determine every single atoms of the viruses, and also we identify some metals in these structures, and this virus will infect the fish group. Okay. So next, I will introduce you the second virus that we work on, which is in fact the shrimp, and so it's a class 3 here. So our target is two virus target. One is to infect the microbranching we call the Thai prawn, and the other was tetanus species. And this virus, we call the white shrimp. The other virus affect this white shrimp. So two kind of viruses affect individual shrimp. Okay, microbranching and tetanus. This is a different shrimp and very economic value shrimp. I think everyone like to eat shrimp, right? But during the infection, and it causes the shrimp die on some disease by infecting the. You can see these two shrimp. This is a healthy shrimp. You can see the transparent, but in the right hand side, you can see the tail become milky and become white, and we call the white tail diseases. And so after the virus infected, the shrimp of the tail of the shrimp become white and milky, and then cause the mortality of the shrimp. And again, this is the virus we call the T3. It's a T3 virus-like particle, and it's the monovirus family, and made up 180 subunit capsid. Okay? So this is an infection, and you can see from the lower part, you can see the tail is still transparent, but it starts to infect it. And so this is the median cases. You can see start milky tail start to see, and this is already completely white tail. And of course, this fish would die. And then so this is I took this picture in the market because the farmer, they are picking those dead fish, the dead shrimp. By picking the shrimp, you can see all the tails getting white. Okay, so it means that those fish are got infected by the notavirus. It's unhealthy or dead shrimp. So again, we constructed the sequence, and based on the we call the PBMV, in fact the white shrimp, and MRMV, in fact the microbranching Thai prom, and you can see the sequence comparison. You can separate two domains. One's a shared domain, the other was a pathogenic domain as a fish virus group of virus. And you can see on the shared domain, these two species virus share 62% on the shared domain, but in pathogenic domain only share 17%, which means the available region is still on the pathogenic domain. So we'd like to see how this pathogenic domain was related to the host. So this time we're using both methods. One's a crystallography method, and this will can determine, this method can determine the resolution to very high, beyond 1.5 angstrom, and but in the beginning we are unable to get the whole virus particle crystal in a good quality, so we're using the Chyan for the structure determination on this virus particle, and the resolution go to 3 angstrom. Okay, so later I will show you two methods to combine these two methods to determine the virus structure. So again, you need to purify your protein. This is the first step. You need to purify your protein. So the protein is about 40 kilodalton. So you can see the single band very pure. And then you can check the assembly of your virus-like particle, whether under the negative standing EM, you can see the particle formation. Make sure it's a good shape. And then, but if you look at carefully, you can see in this imaging, you can see the large particle, and then you have small particle here. Also here, you can, on the right side, you can see the small particle and large particle. So it means that during the particle assembly, the capsid assembly into large T3 particle, and also smaller particle we call the T1 particle. And so because we are not sure this is a nature or just without the genome inside. So, but based on this is a life cycle of the virus, I'd like to show you that when non-envelope virus infect the cell, and will do the penetrating and then encoding and transfer the viral RNA into the nucleus, and then replicate, and then synthesize the protein, the viral protein, and then assembly to the whole mature protein, and then releasing the virus mature releasing out. So this is a whole life cycle here. Okay? But our study contains no RNA inside, genome inside, so it's in fact virus-like particle. So for determining the structure of the virus-like particle, we collaborate with Japan using the Chyan, and then this again Chyan also show you the two size of particle. This is a T3 particle, and then the one smaller T1 particle, architecture particle here. So we separate these two particles for structure determination. And so I will show you what's the T1 and T3. T1 is a T1 alpha-hydro virus particle. It's assembly with 60 copy of the capsid protein. So 60 subunit assembly into the T1 particle, which is smaller. And T3 particle, you can assembly 3 subunits forming together as a trimer, and then the times 60. So 60 copy of the trimer become 180 capsid subunit to become a larger T3 particle here. So that's why you see the T1 particle and T3 particle in our imaging. As you can see, this is a T3 particle and this T1 particle, smaller. So T1 particle contains 60 capsid subunit. T3 particle contains 180 capsid subunits. So, but we we have the this so during the Chyan, then we are able to pick up the separate two size, T3 larger size of the particle and T1 smaller size particle, and over a lot of the particles and a number of particles. So this is all in different orientation, and then we can using this for imaging 2D construction, and then making the averaging alignment, and then for the 3D map, and then eventually we can get the good quality of the density map. And this is the T3 particle, and determine at 3.5 angstrom, and T1 particle determine at 3.7 angstrom. So this is T3 and T1 particle. So this is the quality of the density map, and you can see the alpha helix and beta strand. So all the density map and structure, the residues agree well, and with a good fit. So it means we can determine the good quality of the structure. So this is an overall structure that the T3 particle that you have. You can see the from the magnetic EM, you can only see the roughly particle. But if you can determine the high resolution structure, it can locate every atom, single atom in the particle. So you can see the protrusion domain. This is forming the dimer. And then so I label different colors so you can see the different subunits, and they can align very well, and then forming the good particle with the protrusion domain. So this protrusion domain contains only 70% identity with a different species. So this is a very good agreement with our proposed P domain is responsible for the host specificity and recognition. So if you look at details, and you can see the trimer here, we call the subunit BA and AB and C. So you can see AB are similar, and you can see the protrusion domain and then the S domain, and but there's a long disorder region, the N-terminal domain disorder. But in the subunit C, you can see the long arm here very defined, and so this is a protrusion, and this is a S domain and a linker, and this is a calcium ion, two metals, and so we can determine the structure in great detail. And three capsid forming the trimer, and you can be in between the calcium ion will stabilize this interface of the capsid protein subunits with ligation of the aspartic acid, and this is a great ligate. And so this is 3/4 of the 6 calcium ion. So if you compare the alpha notavirus and beta notavirus, also contain the calcium ion, but the calcium in the stream notavirus contain many more calcium. So this is if you look at this is a single protein, capsid protein, and this is a protrusion domain, and this is a S domain, and this is the N arm long arm here, and this is a surface of the virus, and this is protrusion. And if you look at inside, inside the service, here you can see this is a long end arm. This is long end arm was extends very long and then reach to the alternative subunit here to interact. This is an arm also interact with each other, and then you can to stabilize the inner service structure. So this end arm is greatly stabilize the structure, bias-like particle structure, especially inner service subunit. Okay. And as I mentioned that our particle is a recombinant bias-like particle and should not contain the virus genome. But when the protein is expressed in the E. coli, and sometimes when you do when the protein assembly, and they will the end arm will grab or interact with some endogenous RNA nucleic acid inside. So if you look at the density inside the inner cavity, we can still see some density inside, but it's not so clear. But when you look at this red color, it means some density exists in the inner surface. Okay, we are not able to classify this is whether this is a nucleic acid or not, but I think this is some of the maybe endogenous RNA or nucleic acid inside. So if you compare the surface plot, electrostatic surface plot, you can see the blue means positive charge and red negative charge, and then you can see the positive charge here. The residue, it should be the region to interact with the nucleic acid. So it's very this the positive charge residue arrangement agree with this electron density, electron density distribution. So we believe there's some new piece of the nucleic acid interact with this region. Okay. So because our resolution from the Chyan is not high enough, which is only 3.5 angstrom. So we like to see to characterize the detailed structure of the P domain, because this P domain is much important for the host recognition of specificity. So we like to characterize this. So we do the truncation with this only P domain, and we do the truncation and overexpression this P domain, and crystallize. This is the crystal of the P domain, and you can see a lot of nice crystal that we got. And then you can collect the data again at the synchrotron bin lines, and then you can see the diffraction, nice diffraction, and then you can get the electron density very quick, and you can. This is the beta sheet structure, very clear, and you can build this model very quick in 1 day, and you can finish the structure. So our strategy is to study the P domain and in the in white string and the tight palm, and so we compare these two domains and go to crystals, and so we compare this two domains. This is even you express the protein with a single monomer, but because the P domain formed a very tight dimer, so when we determine the structure, the P domain formed the dimer as we see in the bias-like particle. And there's 1.2 angstrom, 1.4 angstrom. You can see in a very great detail of the interaction. You can see that the interaction between each other, and so we can provide more information. And this is the dimer structure of the P domain. Again, if you compare the two sequences here, you can see of the P domain sequence. You can see the variable region here located on the top surface. So this is corresponding to our proposal that the P domain here is responsible to the not just the evolution divergence because of two different species, but this is related to the host specificity. So because we can determine the structure and then to correlate with a sequence, so we can prove that this P domain is important for the function. Okay. Otherwise, if you don't know the sequence here and you have no idea where those residues are located, and then you have cannot any conclusion that of the host recognition and specificity. So this P domain actually is quite flexible. When we determine the Chyan structure, you can see the very variable region, and then it's like a rotation and translation. But when we determine the crystal structure, actually it's a linker region making more flexible. So this linker region is also important for connecting P domain and the S domain here. So another interesting is we like to study the particle polymorphism, because when we assemble the capsid protein particle into the virus-like particle, and we saw two kind of the size of particle, T3 and T1 particle, larger and smaller. And this is a 44-length capsid, but forming two size. So our thinking is whether the genome interaction affect all those sequence, any domain infect the particle assembly. So we do several strategy. We truncate this disorder region, and we truncate this region, the linker region to truncate out the P domain. Without this P domain, we like to see whether this S domain and N arm can still form a particle, or if we truncate this N arm, which is responsible for the genome interaction, and like to see all those contributions. So we first delete the N arm, the N-terminal arm, and grow crystal, and then this the crystal become the structure become the T1. Okay, and when we delete the N arm, and then it become the also T1. Okay, so this is without the protrusion. This is with the protrusion, but without the N arm, and this is a whole complete mature virus-like particle, T3 particle. Okay. So we use Chyan X-ray crystals and also net staining to prove that. Okay, so I'll do some summary, and this is the first structure of the T1 or T3 PBMB stream norovirus particle structure, and then we are able to identify the domain, N arm and linker region, and S domain and P domain, and this dynamic P domain participate the host cell attachment, and also for the capsid assembly. Okay. And flexible N arm and nucleus are the key component for molecule switching between the T1, T3 capsid formation. Okay. So our structure here can provide the opportunity for the design of antiviral and for such as a vaccine candidates, and also because we are able to assemble the capsid in different size of the empty size. So this is I think many people try to using this like a capsule and can carry many therapeutic agent such as a plasmid DNA or some drug for a biomedical application. So this is a three size that we have, and this is the origami that we fourth is the virus particle. There's a lot of the symmetry of the virus particles. Very beautiful structure that one capsid protein can assemble into the large single particle. It's amazing and very beautiful. Okay, and this work is done majorly my postdoc Chen, and the collaborate with Osaka University, and then we have also the BINA taken in the Taiwan Synchrotron and Spring A. So at the end, I would like to show you one final video that overall my summary using the synchrotron beam lines for the research. Okay. So this is a electron gun, generate electron, and then pass through the accelerator, and then keep the energy, and then reach to the booster ring. The booster ring is surrounding the TPS here, and then to boost the energy to 3 GeV energy. And after that, this is a very high vacuum chamber, and so electron speeding circle around this orbital with the speed of light. And then after the beam, electron beam is stable, will transfer to the another, we call a storage ring, which is confined with a lot of the magnets in the orbital, and then generate the synchrotron light. So this electron will generate the synchrotron light and pass through the beam line. This is the light now, X-ray going to the beam lines, and then shooting on the crystal. This is crystal here, and then we get the diffraction. We can determine the bias particle structure. Of course, we can use in some other. You can study some other materials, and then this is brain imaging and protein structures, and some material studies, and imaging of the balanced fossil, and then drug design. Okay. Okay, so this is my final summary, and I hope that I give you all the idea from the how we determine the structure from protein purification, crystallization, and then data collection, and determine the electron density and structure denomination, and then determine the whole isolate particle. And this is, of course, if you're using this strategy, you can apply to the COVID-19. And COVID-19 virus is not so rigid as this particle, but it's a rather multi conformation, so it's difficult to crystallize. But if you can truncate the domain of the all the components inside the COVID-19, you can do the structure, and then you can, using that, you can design the drug or the vaccine development. Okay. So I thank you for your attention. That I think I will stop here, and this work was publishing, and then if you are interested, I can share with you, and if you have any questions, I'm happy to answer. Thank you.
Thank you, Prof. Chen, for the very interesting talk in introducing the facilities in NSRRC, also the Taiwan proton source, and also the application of the facilities in the NSRRC, and also with the proton source, and also very interesting finding in the norovirus for that infect grouper and also a stream. So I think we will open for the Q&A here. Of course, we also would like to thank Prof. Chen just now for the invitation to use the facilities in the NSRRC. So now I will look at the questions that we have here. So there are several questions, Prof. Chen, I will read that.
Okay.
It was the first question from Kevin Kumar. So what are protein expression systems that are suitable for crystallography? And the second question followed by that is, bacterial expression system is powerful enough to study the virus structure if the protein have post-translation?
Yeah, this is some of the concern. I think for these two cases, we just use the E. coli for expression, and we use a sumo tag, and then we're using, of course, we try different his tag column, his tag expression, and tag. So we try different, in the lab we have different expression system, and you just need to try, and then because the folding also purification purpose. And so for this tool, it's sufficient enough. But if you try to expression some virus infecting like a human, like a COVID-19 or some of the other species virus, sometimes you need to using the other expression system. The E. coli might not give you the post-modification result. So some of them are critical, some are not. So, but in the lab, we try different, we will first try the E. coli first. If not, we will try the mammalian cell, and then different expression system. But so far, I think for the COVID-19 or the other species, we need to work harder, because it's difficult to overexpression by E. coli. But if you can truncate the reasonable size or domain, I think it's still achievable by using the easier system, bacterial system. Yeah.
Right. Thank you, Prof. Chen, for the answer. So the following question is from Dr. Charlotte Takakai. I think he's asking very important question here. So thank you for the interesting talk. May I know, since the access to the photon facilities is free, how you get the funding to maintain the facilities?
The funding, that's what I said. It's a mutual benefit. If we welcome all the users to perform the good science, and this is the good science will provide us some credit, and we can use these credits to talk to the government. The government will review the performance of the synchrotron, not just usage, but they like to see the publication and then the outcome of the science. And also, recently they are focused on the industrial application, and so we provide those needs, and the government see that this requirement is the good performance, so they will continue to support the budget, and annually they will support the budget and for research, and then for the maintenance, and even for the beeline construction, the new beeline. So we ask for the budget from government, and by showing that the synchrotron can really help the science community for the good science production and industrial application. So they would like to see those things. So it's like a mutual benefit, and so the better science we produce, and the large funding we get, something like that. So it's like, so that's why we say welcome all the good science come to Taiwan, and then we provide you the best the facility, and then you can produce your best research. So bring home, and then we can next time you can use in better facility, because new beelines or new funding will come in, and then so you keep going. So I think this is a important, very important issue, and so the government realized that this synchrotron is very important for domestic, not just for domestic, but for international user, and also collaboration. It's very important for open the views and the connection to worldwide. So you can see we have a lot of the international users coming here, and not just that, we have the international, we had the foreigner, like a different foreign, like a German institute or different foreigner institute. They build the beelines. They have they get the funding from German and then build the beamline in Taiwan. So because our facility, the light source is good quality, so we attract those international collaboration too. So this is all the funding we have. The most funding come from the government.
This is very encouraging then, yeah. So as long as good science is being done, then it will get support.
Yes. So yeah, that's why we need to keep doing the good science. Yeah. And also we are inviting the new science coming or new users, and then so we have every year we have the user meetings, and we have all the interest group, and then we can try to get the connection with universities and research institutes, and then try to get the connection, and then ask them what they need, and then we can have more budget to build the better infrastructure, so they can produce good science too. Yeah.
That's very, very good to hear that, Prof. Chen. So we have a next question from Dr. Chaya Budiman. So the question is the T1 assembly naturally exists, or it is just assembly found under crystallization or Chyan? The second question is, any chance to increase the resolution of the 3D reconstruction by increasing the number of average particles? And any rules of thumb, what is the minimum number of particles for capsid protein to be average to get the reliable structure?
Okay, I think the T1 particle is an immature particle. I don't think it will have a infectious capability, but in our in vitro assembly in the lab, we see the T1 and T3, but in the mature virus, it's seldom to see. I think it's still there, but it's not just percentage of the mature virus. I mean, in the host cell, like a shrimp, most of the particles in T3 particle. The T1 is very rare, and so I think is a T1 assembly, maybe because less lack of the genome inside, and so I would say this more like a in vitro assembly. But it's very interesting to see how the capsid assembly with a different condition. That's why we try to understand what which domain or which region is important for determining the T1 or T3 or correct or normal assembly. So I think for the mature virus, most of the T3, T1 maybe it's in a lack of the genome and become the T1. So that's what our experience. Yeah. So for the second question is the particle number for the measuring the Chyan resolution. I think this just depends on my experience is it depends on your particle homogeneity, and if you have a machine by yourself, you can continue to measure and correct the particle number, but in some sense the particle number will not reach out to like a proportional resolution, and the number of the particle is, I don't think it's a proportional, and there's some not just non-limitation, but it's the power of the Chyan, and so we need to decide when to stop the particle picking correction. So if we feel that it's not improved much, and by adding the more 10 times particles, and maybe resolution just improve a little bit, just 0.1 or 0.2 angstrom resolution. So it's not worth to do it. So I think beyond 3 angstrom to 2.5 angstrom is reasonable that you can correct the data for this Chyan, no matter how the particle you have. But I think by 2.5 is already in very good resolution. And so, but you can try to continue to go on to collect the data for assembly. But I don't think it's the effort is worthy to, because you have other project to work on. So that's why our particle always like stop at like 3 angstrom also. We don't continue because the machine need to work on some other project, and you can collect another week, but the resolution won't improve that much. Maybe, just as I said, maybe 0.2, 0.3 angstrom. But you spend a lot of time to work on that. You collect a lot of 10 times data more, but not improve as your previous data. So you need to decide when to stop. So that's why we also another factor is the particle homogeneity, and then the size. Sometimes if we include too many unsuitable particle, you will also decrease your resolution or quality. So I think, to me, 2.5, 3 is okay now.
Yeah. All right. So always a decision to make. Yeah.
Yeah.
What can we get, and how much we need to put, the cost and resources and the time.
Resources. Yeah, that's why I said that we don't own the Chyan to, like, in the lab, in the home. So to do, keep doing. But someone will ask you, have you finished yet? If you collect 10-fold data more, will not give you 10 time resolution better. So it's not really worth it.
Followed by the question of T1 and T3. I just realized just now in your slide, the particle that for T3 is like 43,000 particle, but for T1 it was like 476,000 particles.
Yeah.
Is that means that T1 tend to form, the protein or capsid protein tends to form the T1, then the T3 in the solution, or why is 10 times more the particle for T1 than the T3 here?
Yeah, because this is as I say, there's no genome inside. So also the assembly, we are not sure that our assembly is condition is the best. And every time we send, and they need to, when they look at the population, we have the let me see, we have the, that this is some population here. So we pick up the particle, and then of course the size can be determined, and so this is a number was picked in through the grid, and then it happened that this T1 has more particle to pick, and T3 has sometimes broken, and some are the because I think the bigger particle is I think has because lack of the genome inside for the stabilize, and you see something some particle are broken and partial. So that's why we don't get the many particle in the T3, but T1 has more.
I see. All right. Thank you. There's a question from Dr. Sarah. She asked, since you already have the details information on norovirus structures, how the information can be used for vaccine development. Any work has been carried out on this at the moment? Yeah, the capsid, we need to actually this the structure is released, and then I know that some institute they are try to using the P domain, and because the P domain is in the region here, and try to do the vaccine, and with the smallest
most of the people use a whole capsid protein and as a vaccine. But if you know the detail of the structures, you can. Oh, sorry. You can try to truncate the minima region, and which is more stable region, and then as a smaller vaccine strategy, and then using that to try to compete with the virus. And I think for us, the P domain is the most important region. So that's why we try to get the details. But the vaccine is not our expert to do this. So for us, we just interested in the structure work to publish, and then hopefully some company, actually the British company already contacted us, and they like to work on this vaccine and then get the structure, and then to get the try to produce, and but I don't know how the progress they have. So again, for me, I did not think to do this vaccine by myself. Rather, I'd like to distribute those detailed information, like a domain structure, and a domain you can say if you have the production domain here, like let's see in the final. See here, this is the loop region, and then some of the region here, you can even truncate the smaller peptide, and then this will be another strategy. And then but we need to test which one is more important. And by this, we are able to determine the P domain in detail, and then you can truncate this minima domain. In the future, you can even truncate smaller peptide, and then for the test. But this is not our following work. So we hope that someone can pick up and then do this.
Right, thank you, Prof. Chen. We have a last question for today from Siti Noor Ismail. So the question is T1 structure may represent satellite for mRNA. In any chance, do you know if there are any other ways to purify and concentrate virus particles than ultra-centrifugation?
Can you repeat the question again?
The first question is T1 structure may represent satellite mRNA, the virus particle?
Yeah. Oh, the T1.
Yeah.
T1, the T1, we only get for this work, we didn't get the mRNA particle. We only get the PVNV particle. The NRV we couldn't successfully determine the structure in the high resolution, but we had the low resolution, the data. The high resolution only we have is for PBNV, and so the mRNA we only have the P domain structure. Yeah.
I see. So the next, she would like to know whether there's any method to purify and concentrate virus particles apart from using ultracentrifugation.
Oh, we didn't use ultra high centrifuge. We use just using the you mean concentrate, right? Or purify, concentrate.
Purify and concentrate.
Purify, we're using the we're using the first, because this is an overexpression protein. So when we purify the protein, this is with a fusion tag. So this fusion tag is not forming the particle yet. So when we purify the protein, we can purify in a good purity. Okay, so this is a single protein that we have, and is not forming the particle yet. So we can, so when we purify the protein, we get a single protein, capsid, single subunit. Okay. So next we are using the gel filtration to check the assembly, and then we concentrate in the just in the centrifuge, and not separate with the ultra high centrifuge.
Right.
So it's already good, because when you concentrate, you see the your vial contain the protein virus like particle solution, but you can see some jelly-like feeding, and it's forming. And so you concentrate, and then so we didn't use ultra high centrifuge to concentrate, just use a normal way. But when it for purification, using gel filtration, and then purification is just a normal way that we purify from the single protein. Make sure it's a single capsid protein, and then we find the condition to assembly the particle into the so. But before that, we don't know it's a real particle or just a partial. So we run a gel filtration, and then after that we concentrate, and then we using the negative EN to check the quality, and before we do the structure determination. Yeah.
Right. So thank you very much, Prof. Chen, for the sharing. So it comes to the end of our webinar today. So I would like to thanks again, very kind of Prof. Chen to share with us the facilities in NSRRC, and also his research in structural biology using the X-ray crystallography with synchrotron facilities, as well as the CAR-EM technique, particularly in studying the virus, in this case for the norovirus. So please stay with me. We are going to have further sections, but before the further sections, I would like to introduce a couple of activity of the event from MSBMB and also INBIOSIS. So for Malaysia Society of for Biochemistry and Molecular Biology, we are going to have annual conference, the 45th MSBMB conference on the 18th and 19th of August. Please welcome to search the site, visit the site, and join us for the conference. And we're also having a workshop coming in INBIOSIS. As workshop names microbial identifications for the cloning and bioinformatic analysis. It will be run by Dr. Hamidun Gunawan. So feel free to join us, to join the workshop and also the conference. And now I hope that everyone is convenient to switch on your video. So we will have a photo section. Dr. Mel, you will chair the photo section.
Okay, we wait for
Yeah.
more participants first. Okay, everyone, are you ready? Okay, more is coming. We wait for a while first.
Yeah. So also for everyone information, we have 116 joining the Zoom and about 25 joining the Facebook Live. So we are in total, we are having 140 of participants in this webinar. Thank you very much for joining.
Thank you.
So stay here, we still have a photo section here.
Okay, I think, more is coming in. Okay, I think we can start now. Everyone ready? One, 2, 3, smile. Okay, one more time. 1, 2, 3. Peace, smile. Okay, done.
Thank you very much, Dr. Mel. Thank you again, Prof. Chen, for your sharing, and hopefully see you soon in facilities in the NSRRC.
Yeah, please come here.
Hopefully pandemic will go away soon. I think everyone wishes so.
Right.
That we can move freely.
Yeah.
Stay safe, Prof. Chen and everyone. Thanks again. See you in the next webinar.
Okay, thank you. Thank you.
Bye for now.
Bye-bye. Bye-bye.